this episode, we turn to a continuity problem that feels modern on the surface but follows a very old security lesson underneath. Artificial intelligence, AI, systems can seem impressive when they are working well, yet many organizations discover too late that they treated the model as the whole product and forgot that the real service depends on data, settings, dependencies, review processes, and steady performance over time. That matters because an AI capability can become unreliable or even unusable without a dramatic attack or total outage ever taking place. If the training data is lost, if key settings cannot be restored, or if the model slowly drifts away from the conditions it was designed for, the organization may still have something that looks like a working service while no longer having something it can safely trust. For a beginner, this is the right place to start because continuity for AI is really about preserving dependable function, not just keeping a server turned on. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A helpful way to understand AI continuity is to compare it to ordinary software continuity without assuming they are identical. Traditional software often fails in ways that are easier to spot because a service goes down, a feature stops responding, or a system plainly breaks when something essential is missing. An AI system can fail more quietly because the service may remain available while the quality, relevance, fairness, or reliability of its outputs gradually weakens underneath the surface. That means continuity has two sides here. One side is whether the service is still running and reachable, and the other side is whether the service is still fit for the purpose the organization depends on. When beginners hear the topic this way, they start to see why backup and recovery planning for AI cannot stop at infrastructure alone. The organization also needs to preserve the ingredients and conditions that allow the model to behave in a trustworthy and repeatable way after disruption or change. Datasets sit near the center of that continuity picture because many AI systems depend heavily on the information used to train, tune, validate, or update them. If that data disappears, becomes corrupted, becomes mixed up with the wrong version, or can no longer be traced clearly to its source and preparation steps, recovery becomes much harder than people expect. A beginner might think a dataset backup is simply a copied folder stored somewhere safe, but that is only part of the story. The organization also needs to know what the dataset was for, when it was captured, what labels or transformations were applied, what permissions governed its use, and whether the restored version still matches the model or use case it is supposed to support. Otherwise, the backup may exist in name while failing in practice. That is why dataset continuity is not only about storage. It is about preserving enough context, integrity, and organization that the data can actually support restoration rather than creating confusion during an already stressful recovery moment. This is also why version control matters so much in the continuity conversation, even for beginners who are not working directly with engineering tools. If a team loses track of which dataset version was used for which model version, the organization can easily end up restoring the wrong pair and wondering why results no longer make sense. A model trained on an earlier dataset may behave differently than one trained on a later clean dataset, and a dataset restored without its proper structure, labels, or preparation notes may become far less useful than people assumed. The deeper lesson is that a backup should restore meaning, not merely files. In the AI world, meaning includes how the data was gathered, how it was prepared, and how it fits the specific model and business purpose. For beginners, this is a useful shift because it turns backup from a storage habit into a continuity discipline. The real goal is not simply to say we save the data. The real goal is to restore the right data in the right form with enough context that the organization can resume trustworthy operation. Configuration recovery is the next major piece, and it is often underestimated because settings can look less important than the model or the data itself. In reality, configuration tells the system how to behave, how to connect, how to enforce limits, how to apply rules, and sometimes how to interpret or route the inputs and outputs flowing through the service. If those settings are lost, altered, or restored incorrectly, An organization may bring the service back online in a form that behaves very differently from what users, reviewers, or managers expect. That creates a serious continuity problem because the service may appear restored while quietly operating with the wrong thresholds, the wrong access conditions, the wrong integration points, or the wrong safety boundaries. For a beginner, the lesson is straightforward. A model does not live alone. It lives inside an operating environment shaped by configuration, and that environment needs to be recoverable if the organization wants the AI service to return in a dependable way rather than as a rough approximation of what used to work. Configuration continuity also matters because AI services are often surrounded by other systems, business rules, and support processes that influence the real outcome. A model may depend on input formatting rules, approved prompt structures, routing logic, validation steps, confidence thresholds, access restrictions, and escalation paths that tell staff what to do when output looks uncertain or risky. If those supporting conditions are not preserved or restored properly, the organization can lose more than technical performance. It can lose the governance and operational discipline that made the service safe to use in the first place. Beginners benefit from hearing this because it prevents a narrow view of recovery. You are not only recovering the model, you are recovering the working arrangement that allowed the model to support the mission in a controlled and understandable way. When configuration recovery is neglected, continuity weakens because the organization may reintroduce the service without the same guardrails, review habits, or usage boundaries that once kept it acceptable. This is where business continuity, BC, and disaster recovery, DR, help create a useful mental frame. BC is concerned with how the organization keeps essential work going during disruption, even if the method becomes slower, reduced, or more manual for a time. DER is more directly concerned with how systems, data, and technical capability are restored after a disruption so the organization can return to stronger normal operation. In an AI setting, BC may involve deciding how a team continues serving customers or reviewing content if the AI system becomes unreliable or unavailable for a period. DER may involve restoring the correct datasets, model versions, configurations, and supporting systems so the capability can return in a trusted state. For beginners, that distinction helps a great deal. It shows that continuity is not only about getting the model back. It is also about deciding what the organization does in the meantime so important work can continue without unsafe dependence on a damaged or uncertain AI service. Model drift brings a different kind of continuity challenge because the service may remain technically available while gradually becoming less aligned with the real world it is supposed to support. Model drift refers to a change over time in how well a model fits current conditions, current data patterns, or current operational reality. The model may not be broken in the usual sense, but it may start producing weaker classifications, less useful recommendations, less accurate summaries, or more unstable results because the environment around it has changed. This matters because continuity is not just about recovery after a dramatic event. It is also about preserving dependable performance over time as the world moves on. For beginners, this can be one of the most important ideas in the episode. A service can be up, reachable, and still failing in a quieter way if drift has reduced its ability to support the task it was built for. That makes drift a continuity issue, not merely a quality issue sitting off to the side. A simple way to hear model drift is that the system learned from one set of conditions, but the real world later shifted enough that the old pattern no longer matches well. Customer behavior can change, language can change, fraud patterns can change, normal usage can change, business processes can change, and external conditions can change in ways that slowly pull the model away from what it once handled effectively. The important point is that this does not always happen all at once. Drift can arrive gradually, which makes it especially risky because confidence may remain high long after performance has begun to decline. Beginners sometimes assume failure will announce itself loudly, but AI continuity often weakens through subtle mismatch rather than sudden collapse. That is why responsible organizations pay attention not only to whether the system is online, but also to whether the outputs still fit the environment, still support the mission, and still deserve the level of trust users are giving them. This gradual drift can harm continuity in very practical ways. A customer support assistant may start giving less relevant guidance because products, policies, or user questions have changed. A detection model may begin missing important patterns because the normal behavior it learned no longer reflects current traffic or threat conditions. A review model may become less fair or less consistent because the data flowing into it has shifted away from the cases it was originally tuned to handle. In each case, the organization may experience a functional loss even if the platform remains fully available. That is why drift belongs in continuity planning right alongside backup and recovery. It affects whether the organization can keep using the AI service with confidence or whether it must slow down, fall back to manual review, or suspend use while investigation and adjustment take place. For beginners, this reinforces a vital lesson. Availability alone does not guarantee continuity if the outputs have drifted far enough to become operationally unreliable. A strong beginner mindset is to treat AI continuity as a chain that includes data, configuration, model behavior, ownership, and fallback operations rather than as one technical object. If any link in that chain is weak, the organization may struggle during disruption or gradual decline. Dataset backups need to be accurate, protected, well-organized, and meaningful enough to support restoration. Configuration recovery needs to bring back the operating rules, settings, and integration details that make the service behave as intended. Drift awareness needs to tell the organization when the model is still running but no longer aligned well enough to be trusted for the task it serves. This chain view helps because it moves the conversation away from simple uptime and toward dependable service. A beginner who thinks this way is already stronger than someone who assumes that if the endpoint responds, the continuity problem must be solved. In AI, continuity is about whether the service remains both reachable and worthy of operational reliance. Testing matters here just as much as it does in other continuity topics, because backups and recovery plans can create false comfort if they are never exercised in a realistic way. A dataset backup that cannot be matched to the right model, a configuration package that restores outdated settings, or a drift response plan that no one knows how to execute will all fail when pressure arrives. This is why organizations benefit from practicing recovery steps, checking that restored versions behave as expected, and defining how staff will respond when the model becomes questionable rather than fully unavailable. Beginners should notice that this is not about perfection. It is about reducing surprises. Testing exposes missing documentation, unclear ownership, outdated assumptions, and hidden dependencies before a real disruption forces the team to discover them the hard way. The more often continuity plans are reviewed and exercised, the more likely it becomes that recovery will restore a genuinely usable AI service instead of a technically present but operationally confusing one. There are also a few common misconceptions that beginners should leave behind. One is the belief that if the model file is preserved, continuity is covered, even though the model may depend on very specific data conditions, settings, approvals, and workflows to remain trustworthy. Another is the assumption that cloud hosting automatically solves continuity, even though the organization still needs recoverable datasets, known configurations, clear ownership, and a plan for drift. A third is the idea that drift is merely a performance tuning concern for specialists rather than a real operational risk. In truth, drift can quietly reduce service quality until teams are forced into reactive decisions under pressure, which is exactly what good continuity planning is supposed to prevent. For a beginner, these misconceptions are worth clearing away early because they help replace shallow confidence with practical awareness. The aim is not to fear AI. The aim is to understand what must be preserved and watched if the service is going to remain dependable through change and disruption. As you think about scenario questions or future workplace discussions, a very useful habit is to ask what kind of continuity weakness is actually present. Has the organization protected the data needed to restore the service meaningfully, or only the most obvious files? Can the team recover the settings and operating rules that made the AI capability safe and useful, or will recovery produce a loosely similar but less controlled service? Is the model still aligned well enough with current conditions to support the mission, or is drift slowly pushing it out of acceptable range? These questions help you reason more clearly because they separate storage problems, recovery problems, and performance alignment problems that might otherwise blur together. For beginners, that separation is powerful. It turns a modern-sounding topic into a set of practical security and continuity judgments that can be applied calmly without needing to become a specialist in every technical detail. As we close, remember that protecting AI continuity through dataset backups, configuration recovery, and model drift is really about protecting dependable service over time, not just protecting files or servers in isolation. Dataset backups matter because the model depends on the right data in the right form with the right context if meaningful recovery is ever needed. Configuration recovery matters because settings, rules, and integrations shape how the service actually behaves after restoration. Model drift matters because an AI system can stay online while quietly becoming less reliable, less relevant, or less safe for the purpose it serves. When those three areas are understood together, continuity planning becomes much stronger and much more realistic. That is the foundation a beginner should carry forward. A trustworthy AI service is not preserved by uptime alone. It is preserved by protecting the information, operating conditions, and ongoing alignment that allow the service to remain useful when disruption happens and when the world around the model keeps changing.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.